and thank you for recreating the journey. Thank you to the department. For 7.5 decades, you're guiding the water and having us aboard on the deck of the ship, really, and planting us to the different places that we took our life journey. But the bonding and the attachment is so great that we come back to reflect on what we learned. And John Dewey, the philosopher of 20th century, US, most famous one in US, he said, I was reading the other day, you don't learn from experience, you learn by reflecting on the experience. So here we are, reflecting on our experience, and I was racking my brain for what you remember from your days at IISc. The couple of images that pop up is, of course, your gurus. And Prof. Gandhi, fluid mechanics course, first day, first show of movies. I don't know how much I carry that, but that made some impression. And he was talking about mundane objects like water, different ways of looking at water. That was what we learned in fluid mechanics. And of course, Guru's Guru, Professor Kumar, late Professor Kumar, he taught us population balance equations to look at nanoparticles, like you lazy fellow, nasty fellow, how to model them, how to use them. So I hope I'll connect some dots there today, take up water and show you some efforts we have made to understand them through nanoparticles, and that's where our journey starts. So this is work which I have been doing with my students over the last 5-6 years. So when you look at a water drop, really, Avogadro number of molecules. But even a single E. coli cell is not welcome there because it grows and causes disease. Same with other molecules which are in Indian water systems like arsenic, fluoride, and literally 1 in a billion or a 1 in a million. In case of arsenic, it's ppb level, so 1 in a million, and in case of fluoride, it's 1 in a billion ppm level. That is not welcome. So we look at how to detect them, how to measure them. That's the first question, and how to remove them. Some of you have heard these from me in a couple of years time before. So pardon the repetition, but we'll try to see some new results today. So as I said, connecting the dots, the particles, the specific surface area is what we are interested in, which scales inversely with the diameter of the particle. And of course, being chemical engineers, my personal interest in chemistry and materials, we try to functionalize the surface, the large area, because of the defect sites. So we take help of the physical size parameter and the chemical surface parameters to do new chemistry and hope to do something better. So one example, I'll share 2-3 short stories given the time. So one short story is here. So this is, imagine this is a gold particle, which is shown here, individual particles. Now, there are some functionalization called molecules, methyl cobalamin, which have a propensity to catch arsenic, which is a red dot here. And when it sits on these, the red dots on the gold, because arsenic is +3, it brings 3 gold particles together because of the functionalization, and that results in aggregation. So basically, you start with single gold dots, which are shown here as a black size distribution of around 8 nanometer particles. When you functionalize, it is this red distribution, 10 nanometer, that is this object, going from this object. And then when you throw in arsenic, then you get an aggregation, which is shown here, small particles aggregating, same scale bar, and shows up here as a broader distribution of 20, 30, 50 nanometer diameters as you increase the arsenic concentration from half to 10 to 100 ppb. So it becomes a signature of how much arsenic is there. And because this aggregation is related to the surface plasmon resonance effect, which is well known in literature, there is an increase in the absorbance peak of this gold nanoparticle, and that is used as a signature for tracking arsenic concentration. So you have absorbance of arsenic as a function of arsenic concentration going up linearly pretty well. At a higher concentration of arsenic, it saturates out, but nevertheless you have an operating curve where if you measure the absorbance, you can invert out the concentration on the x-axis. So that becomes a calibration plot, if you like. And good thing about it is, because of the specificity of the reaction, it picks up only arsenic and gives a high absorbance, whereas all other metals and ions which are normally present in water, starting from the heavy metals or the inorganic anions, give no or very, very low negligible signal, same as the controlled pure water sample. So that brings in linearity or the sensitivity of the system, and this brings out the specificity of the system. That's what you want to do when you sense something. So we went ahead and did some work with different sources of water in and around our lab in Mumbai, in rivers, and we standardized with ICP-MS, which is the gold standard for measuring concentrations. And you could see everywhere for different TDS of water, which is different kinds of water, this specificity shows up. So when you have acceptable arsenic of 1.18 ppb, our system gives 1.3 ppb. Any other unacceptable arsenic of 18 ppb, which is more than 10 ppb, because WHO limit is 10 ppb, it gives 17.4 ppb. So fairly good enough. So we did these kind of things for other systems like fluoride, chromium, iron, etc. And to cut a long story short, we came up with, rather the students came up, all credit to them, they came up with some lab devices, handheld devices for a single, this is a single tracking, this is for multiple tracking where you can make. Long story short, we came up with, rather the students came up, all credit to them, they came up with some lab devices, handheld devices for a single, this is a single tracking, this is for multiple tracking where you can measure, we have a LED and photo transistor system where you put in the water sample, turn on the dial, and you can measure the concentration of the contaminant in a matter of 4 minutes, which is the optimum reaction time. So those optimizations have been done so as to have it as a handheld device which can be used on the spot, okay, in about 4 minutes time to detect any of these metals or fluorides. We have worked with 4 so far. And then there was other projects where we want to do remote sensing. So this is a device in the Jalviar pond of IIT Guest House, IIT Bombay Guest House, which is a continuous version of this batch system of measurement, if you like, which this year the students went and did measurement. This is near Kozhikode, Konoli Canal, which is where we planted this device. So this is entirely made in the lab by the students through 3D printing and all that. And this samples water from the canal, and the water is pumped in, and then you can see the motor running, and there is these reagent bottles through which the water flows, and the reaction happens, whichever it is, and then it is measured and transmitted remotely through a low-range communication system. And this is supposed to work uninterrupted as long as the battery power runs. And so this is where we are right now. So it is still requires further development to work uninterrupted for a long time. But that's what we call it Aquasis, autonomous wireless sensor network. So the idea is not only chemical parameters, but physical parameters also. So we have gone ahead with this is pH, temperature, oxygen reduction potential, dissolved oxygen, etc. That's in the pipeline. So a water monitoring station which can be used for monitoring water quality, just like air quality is of concern in Delhi, Mumbai, and other big cities. Coming next to the second story, which is water treatment. So we were interested in nanoparticles all the time. So what we optimize conditions for high reactivity, stable, long-lasting applications, and identify characteristics of particles by which you can put these particles on substrates, because only particles will flow out and will not last long, but immobilize them on surfaces like carbon, for example, which is a universal water filter medium. So we did all that, and just to illustrate, so for example, this is carbon, which is used in our filter media, large number of pores, which are used for removing color, odor, and smell, and chemicals, but not E. coli, because E. coli feeds on the carbon. So you need to put something else. People have UV power switches, but when there is no power in rural or other areas, is there any additive that you can use? One additive which we have tried is copper and silver combination. So these nanoparticles, if you put on the carbon, and then the carbon, we do functionalization so that the nanoparticles don't go inside the pores of the carbon. This is one among many pores of the carbon. And the nanoparticles are sitting here. So when the E. coli flows through the across the surface, it comes in a good contact through this copper, and the copper does what it does. And what it does is here, if you see there are three panels. This panel is for silver, all are in function of time. This is silver on the carbon, what it does to the E. coli cell. This is copper on the carbon, what it does, and this is combination. So by serendipity, we saw silver does a good job of killing the cell, copper also does, but silver-copper combination does a better thing. And why? Because as you can see the time scales here, silver takes 25 minutes to completely destroy, copper takes 10 minutes, but there is some synergy when you give silver and copper is 8 minutes. So going from 25 to 8 minutes, there is a factor of 3.5, which enhances the kill rate, and that translates directly to 3.5 times larger throughput of treatment of water in a filter in a domestic batch quality. And what is the reason? The reason is there are two steps really. First step is the nanoparticle deforms the E. coli surface and forms small pits. This is the first step. You can see in all cases. Here the pit formation is faster. It is taking 7 to 2 minutes, and that's why the job starts faster. And then the second step is once that happens, the copper or silver ions, which have finite but small solubility in water, moves inside the cell and does intracellular reaction, producing reactive oxygen species, and which is what interferes with the metabolic pathways and prevents DNA and replication, and the cell basically goes to an apoptotic phase, which is basically it just falls off. Okay, and so overall there is a enhancement in rate, and like good chemical engineers, we recognize there is a rate controlling step. Okay, and that is seen here in case of silver. It takes 20 minutes to form the pits, literally, and then the action starts, the intracellular reaction, which is the ion-induced reactions. Whereas in case of copper, the rate-limiting pit formation first step is not there. It's the intracellular reaction is slower. So you have a combination of silver copper, then the copper opens the door of this room, okay, and silver does the job of doing the intracellular reaction faster. So that's why there is a synergy. And we are now testing a 20-liter system in the lab where you can store 20 liters of contaminated water. It flows enters through this filter column, driven by gravity, flows upwards, there's good contact time. So what comes out and is collected in this jar. And we are doing the breakthrough curve analysis and all that. So the idea is enhancing the throughput and without power, a gravity-driven system. So of course, it's not commercial or anything of that sort, but we are excited by the science of synergy and thought that that uncovers a new pathway of getting rid of these E. coli or others cellular material. The last is E. coli or others cellular material. The last thing I wanted to tell is about catalysis, but I think we are already running short of time to this morning session. So I will skip that and directly go to the conclusion, which is we talked about on-spot rapid handle sensor devices for autonomous monitoring of water quality parameters, and then we looked at some synergy between the systems leading to high water throughput. And the last one, which I just say as a conclusion, we saw some effect of shape and pore orientation in these particles. So I talked about solid particles. The last part was introducing pores in the particle and doing impregnated nanoparticles, where we found a new effect of shape and orientation also can play a major role in enhancing chemical reactivity. So what I believe is shape-induced effects of solid-state catalysts on reactions have not been studied. That can be a new tool. Just the last part as a future, what we are doing right now is, if you look at this is the last slide, that if you look at this filter column, you will see that these packed granules of carbon. If you continuously zoom into the system, you will see these nanoparticles are decorating the outer surface of these solid particles. Black dots are the silver and copper, if you like. And when water flows through this, it goes through meandering path, and then we model it as an individual pore lined up with these particles. And E. coli cells are flowing in, okay, and so they go through this tumble motion of run and scoot, and in that process they come in contact with these nanoparticles. So our job is to maximize the contact of these E. coli in this case with the internally impregnated particles. So what we thought is we will look deep into it, and since the filter column is black, as you saw, because of carbon and you can't see, so we say we'll do some experiments in a single channel and try to understand the individual part cell level behavior. Because what we see in a filter column is an ensemble behavior of 10 to the power 4 E. coli per ml, which is a model of a contaminated water. But what you want to understand is how a single particle dynamics is, and following a single particle trajectory will give us insights to go back and design the column more effectively. So very recently, just last year, we have started this experiment, and that we made a channel, microfluidic channel, and then we flow these E. coli laden cells in the inlet here, and they come out through this outlet. In the process, we tag the E. coli and watch their movement. So this is a empty channel in PDMS, and this is a channel containing copper nanoparticles. You can see copper nanoparticles in PDMS, this PDMS. So we are tracking the particle as the cells. The idea is the cells must be sensing the presence of particles and doing something differently in their tumble and scoot motion. And we just tracking the mean square displacement with time. I'm sorry the legend has not come very well. Basically, it is all are individual particle trajectories. And we find that the diffusivity, which we get from the mean square displacement, is about 30% less when you have copper in the channel versus when there is an empty water channel. So we believe that there is something the E. coli flagellars are sensing differently in presence of the nanoparticle and trying to avoid their proximity to the wall, because they know that near the wall they are going to die. And our job will be to prevent that and accelerate the motion. So how, we don't know at this point, and that is what our future holds for us. So I think I'll stop there, and thank you again for coming on this afternoon.
Thanks, Prof. Thanks, Prof, for the nice talk. Yeah. This is regarding a question regarding the silver and the copper. So in the literature, there is two schools of thought. Which one is the silver ion which is playing a role, or is the silver nanoparticle? I'm just curious, what is your view on which is dominant? Because always they correlate the ion is playing a major role.
Yes, exactly. So this is a debate ranging from around 2010 to 20 almost. There were two schools of thought, as you exactly said. One is called Lichkin, Another is called contact kill. Contact kill is just the solid particle the E. coli is getting, kind of eroded or pitted and gets. It's a biophysical process that the membrane falls off. The other school of thought is no, the ions too. So what we found, we did experiments, control experiments, that both are important. The ion kill is more. So we just put dissolved ions and let it do the job. And we also do particles where both particles are not doing the job. We figure out that about 60 to 70% is by ion killing and about 30-40% is leaching. So both are important. And that's why I showed that in the image panel, which explains the two steps. And we did these fluorescence measurements, which is the next slide where I showed the rate. So, and in this case, we discovered that there is a synergy, because in one case, silver does one faster, the copper does the pitting faster. So there is a synergistic effect, which alone will not show up. So that's why I think we are excited about that part of it.
Sir, I had a question exactly on the similar point. So you mentioned that the bactericidal activity is because of reactive oxygen species which are produced.
Yes.
So in one of your slides, I saw that you are also using L-ascorbic acid.
Yes.
So I just wanted to ask, is L-ascorbic acid being a potent antioxidant, is it going to inhibit the bactericidal activity?
No, so L-ascorbic acid is used for synthesis of the copper.
Okay.
So L-ascorbic acid is a reducing agent as well as a stabilizer to get the 5 nanometer copper. But then when we put it on carbon, that is, concentration is very less. It is washed and clean because carbon itself immobilizes them. So there is no question of further having them to provide the stability which is required in a liquid dispersion. So in the final product, it is almost not there. And it's a food grade, so it is, so it is, the traces are fine. Yeah.
Thank you, sir.
I now request Dr. Bharti to present an intro to Dr. Rajdip Bandyopadhyaya.
Thank you.